All right, we're just going to look at a couple more types of reactions of alkenes. And technically, these kind of fall under addition across a double bond. They're just a little weird. They kind of don't feel a little, they don't feel similar. But if we look at the mechanisms, then you can kind of see how these fall under this concept of we're adding stuff across a double bond. But the first of these we're going to look at is known as oxidative cleavage. This is where we're going to take an oxidizing agent, and not all oxidizing agents do this, but so I'll highlight the ones that you need to know. But certain oxidizing agents will completely cleave the double bond in half. And the short thing that I want you to know is that you're going to give each carbon of the double bond, I should say, make each carbon of the double bond a carbonyl. So I'm going to highlight this carbon, and I'll use a different color here, that carbon. And I'm completely splitting these two things apart. So I'm drawing it like this. And I'm making this carbon here a carbonyl. And I'm making this carbon here a carbonyl. Now it's the same exact product. And so if like you just sort of say, oh, all I'm going to get is this, that's fine. You can draw it like that. I'm just emphasizing where everything is going and where everything is coming from. Now, this kind of reaction is known as ozonolysis. And as the name implies, we're going to be using ozone to accomplish this. So let's look at another example here. So the reagents that you need to know, we're going to use ozone, O3, and then a second step of zinc and water. Now, I'm not going to require the mechanism for this reaction. I highly recommend looking it up in your textbook. Just spend like 5 minutes reading it, and you'll see that the first step involves adding stuff across the double bond. And then you'll be able to see like how it gets all broken up into two pieces. But I'm not going to require it. I won't go through it in this video. But what we're going to do is we're going to split the double bond apart. And I'm going to give this carbon right there, I'm going to make it a carbonyl, and I'm going to make this carbon a carbonyl. So I'm going to draw the two pieces just kind of like how they appear in the reactant. And so this carbon gets a carbonyl, and this one gets a carbonyl. So in this instance, you'll see here that I've made a ketone and an aldehyde. We can even draw on the hydrogen there just to emphasize, that's an aldehyde. Now, another thing that I can do with this, it's a very similar process, but if I change the oxidizing agent a little bit, the outcome may be different. Oh, that's not two steps. So if I change the oxidizing agent to potassium permanganate, that's a really strong oxidizing agent. And if one of the sides to an alkene has a hydrogen on it, so I'm going to draw that one specifically there. When I break this alkene apart, the left side here that doesn't have any hydrogens, still a ketone. But because there's a hydrogen there on that right side, instead of oxidizing to an aldehyde, it gets oxidized to a carboxylic acid. So that will occur, as I said, if there is a hydrogen on either side of that carbon-carbon double bond. If there weren't a hydrogen there, like if I go back up to this first reaction, this alkene did not have a hydrogen on either side, I could use potassium permanganate and I would get the exact same products. So KMnO4 only affects it if there's a hydrogen on the carbon of the double bond. Alternatively, you might see this in some textbooks. You can still use ozone, but instead of using zinc, if we use another oxidizing agent like hydrogen peroxide, that will do the same thing as potassium permanganate. Now, the last reaction that we're going to work on, and then the next videos that I do will just be practice for the exam. Um, we're going to look at making cyclopropane from alkenes. Right, so one of the ways that we can accomplish this, here's an alkene. We're going to react it with chloroform, CHCl3, and potassium hydroxide acting as a base. Now, don't worry about, again, don't worry about the mechanism for this. You can take a look at it in your textbook. It involves an intermediate known as a carbene, and I'll talk about carbenes just for 1 second here. Carbenes are interesting because it's a carbon that's missing electrons, but it has no charge. So it's carbon with a lone pair, so it's not negative, and even though it's missing electrons, it's not positive. So it's kind of got traits of both a carbanion and a carbocation, but it is not charged. It's a neutral chemical species. And one of the ways that carbenes are made is to use this process right here of reacting chloroform with potassium hydroxide. And that's going to add that carbon, I'll highlight it here. This carbon of chloroform is this one here. And then they'll have a couple chlorines on it. Now, alternatively, if I didn't want those chlorines there, I do a little bit of a modification and use CH2I2 and an alloy of zinc and copper metal. This particular reaction here at the bottom is known as the Simmons-Smith reaction. Do you want to, take a quick look at it in your textbook? It does the same thing. It's just you don't end up with any halogens on the carbon. So this carbon right here is this carbon right here. All right, so very quick, very easy. All you're doing is just adding, making a cyclopropane ring across the alkene. And as I said, you do not need to worry about the mechanisms at all for these last two reactions that I've talked about. In the last two videos for this day of lectures, I'm going to be doing a bunch of practice. So it'd be very important to watch those videos. In the last one especially, because I'm going to go through multi-step synthesis now that we've talked a lot more about reactions in this chapter.